Let us now discuss enzyme inhibition, or what are the kinetics of enzyme inhibition. So by enzyme inhibition, as we discussed already, that there should be some other molecule, which is other than the substrate, that actually binds to the enzyme and reduces the probability of the substrate going into the product. So you can write the equation like there is of course an equation with the enzyme and substrate as before. So you can write the rate equations like this, and then I have enzyme substrate complex which forms the product. Now the enzyme can also bind to an inhibitor, and we call that complex an enzyme inhibitor complex, and it has some equilibrium. Instead of writing the rate constants, you can just consider the equilibrium, and usually this equilibrium constant is written as Ki because its I means actually inhibitor, and the equilibrium constant is written in the reverse way. In the sense, it is the equilibrium constant for the reverse reaction. If this EI to E plus I is the forward, and the E plus I is the backward or reverse reaction, then the equilibrium constant can be written as concentration of E into concentration of I divided by concentration of EI. Now you see one interesting thing here. So what I'm saying right now is that the enzyme has a particular pocket, and a substrate can bind to it, but not only the substrate, an inhibitor which also has the same size and shape can also bind to it. Then if this binds, then I'll have the enzyme substrate complex, and if this binds the inhibitor, then I'll have the enzyme inhibitor complex, which will look like this. Now this means actually the substrate and the inhibitor competes among themselves for the active site. So this kind of inhibition is known as competitive inhibition. Competitive inhibition. Now let us try to understand what will be the rate law, or how the Michaelis-Menten equation or the Lineweaver-Burke form of Michaelis-Menten equation will take the form for initial rate versus initial substrate concentration. Now let us consider that as before we are going to use the steady state approximation for the enzyme substrate complex, and that would be 0, and that is nothing but, as you know, that enzyme substrate complex appears here, so it will be K1 ES, and then we'll have minus K minus 1, sorry, it is forming ES, so it will be K1 into E times S minus K minus 1 into ES minus K2 into ES. So that is 0 under steady state approximation. Then as before we proceed, we can actually calculate the material equilibrium. So at any point the concentration of the initial concentration of the enzyme will be the amount of the enzyme present at that time plus some amount of enzyme is forming the enzyme substrate complex, some amount is also forming the enzyme inhibitor complex. So we can write for, and the enzyme inhibitor complex we can also write it like E plus ES plus, we can use this equilibrium, so we can write it as E into I divided by Ki. So you can see that I can take the enzyme thing common here, so it will be this. I'm just skipping a step, so if I move this term on the left, it will be, and just switch my left to right, it will be E0 minus ES, and then it will be divided by 1 plus, because for the enzyme term I'll have 1 plus I by Ki. So that is the solution for enzyme concentration at any time. Similarly, we can also write the substrate concentration in the similar way, and substrate concentration will be nothing but the free substrate concentration plus enzyme substrate complex plus some substrate has given rise to product. So this will be the same as the Michaelis-Menten equation. So we can right or right, it will be S0 minus ES minus P, and this ES thing we can ignore always, and the P thing also will ignore eventually. So this will be nothing but S0 itself in the limit t tends to 0, because only in the limit t tends to 0 this term goes to 0, and ES we can always assume is much smaller than S0. Now let us say that what will be the we can actually put the values here and try to figure out what is ES. So this is under steady state as well as t tends to 0. I'm writing both together. So this will be K1. Instead of E, I'll write E0 divided by 1 plus I by Ki, and minus ES. I'm just separating the terms, because I'll just collect the terms which are ES, enzyme substrate complex, 1 plus I by Ki. This will be I, concentration of I, and then I have S. S is nothing but S0, already you know that, and then I have minus K1 plus K2 into ES, that is equal to 0. So I have to collect the terms for ES. So the ES will be nothing but this term which is left, which is K1 into E0 into S0 divided by 1 plus I by Ki. Let me actually write it here because it's a big term. And then divided by the common part which is coming with Ks. You can see here it had basically it had 1 plus, so Es is multiplied by, as you can see, 1 divided by 1 plus I into the concentration of I divided by Ki plus K1 plus K2. It will be K minus 1, not K1. And this is a concentration term. So you see, this is the expression for ES. We can actually multiply the numerator and the denominator by 1 plus I by Ki and simplify this form. Let us do it. So it will be nothing but K1 E0 into S0 and divided by, I'll have, if I do that, so the first term will be 1, and then I'll have K minus 1 plus K2 times this entire part, which is 1 plus I divided by Ki, And then we can further divide everything by K1 into E0 as we did earlier. So in the numerator and the denominator, and then we'll have or we can actually keep that at this stage, and we can do it later also, because the I mean, just for material balance, you see that K1, it will be K1 K minus 1 plus K2 divided by K1, and that we can just keep it for the time being. We can get back to it later also. Or in the Michaelis-Menten part, the way we did it, if we go back, so we actually divided by K1 into S0, so that we can do. So this K1 and this S0, that is remaining here. So that K1 into S0 combination, we can divide the numerator and the denominator in this case, but we are missing one K1 S0 here. So let us see where is the K1 into S0. So this constant, the way we have written, this is this, plus when we collected the terms, there will be a K1 into S0. As you can see that this term for ES, maybe we can write it clearly in one more step. So this is nothing but first write the term which is the constant term. It is K1 into E0 divided by 1 plus I divided by Ki, and then I'll have all the ES terms, but then the first term of the ES also has K1 and S0, so it is K1 into S0 divided by 1 plus I by Ki, and then there is K1 plus K2 plus K1 plus K2, it is K minus 1 actually, and that multiplied by ES, and this is equal to now the rearranged form. So you can just draw a line just to avoid confusion. So that gives, this is the ES concentration. So you can divide numerator and denominator by K1 into S0. So this is, at this stage, is K1 into S0, and if you do that, so then I'll have here K minus 1 K2 by K1. Maybe we can go to the next page and write, or maybe we can write it here. So I'm writing the next step. So we'll write it as dividing the numerator and denominator by K1 into S0. So we'll have nothing but E0 divided by 1 plus, now K1, K minus 1 K2 plus K2 divided by K1, that we called as Michaelis constant Km, and then we'll have divided by S0 multiplied by this factor, which is 1 plus inhibitor concentration divided by Ki. Now let us write it very clearly. So what we got is the enzyme substrate complex concentration under steady state at t tends to 0 is nothing but K1, K1 into E0 we already removed. It is E0 divided by 1 plus Km by S0 into 1 plus I divided by Ki. So the rate of the reaction, or dP dt, at t tends to 0 is K2 into Es, which is nothing but, so the K2 will be multiplied, and we know that K2 is nothing but, K2 into E0 is nothing but Vmax divided by 1 plus Km divided by S0 into 1 plus I by Ki. Now let us just plot the Lineweaver-Burke plot for this competitive inhibition pathways. So as before, let us just draw. So of course, if I plot here, this is actually V0. It's still not written in the Lineweaver-Burke form. The Lineweaver-Burke form, if I write it, it will be 1 over V0, and it will be 1 over Vm, plus it will become divided by Vm into 1 plus inhibitor concentration divided by Ki into 1 over S0. I am writing the 1 over S0 slightly differently. And then we are plotting 1 versus V0, 1 by V0 versus 1 by S0. And then let us try to understand what is the nature of the plot. Now suppose, again we will do the y-intercept and x-intercepts. Y-intercept means actually x is 0. So if I put that as 0, this entire thing goes to 0. And then the value of 1 over V0 is the same. It is 1 over Vm. So this intercept is nothing but 1 over Vm, always. Now, if you ask what is the value of the other, if we just extrapolated it, at what point it crosses the x-axis, for that we have to take 1 over V0 is equal to 0, because that's the x-intercept, and at that point what is the value of 1 over S0, that we can easily figure out. We take it to the other side, it will be minus 1 over Vm. So that Vm and this Vm cancels, and now this Km will be brought down, so it will be 1 over Km with a minus sign. It will be minus 1 over Km into, we'll have also this other factor, because we are just writing the 1 over S0 term, and it will be exactly 1 plus I divided by Ki. So it's not just 1 over Km as in the enzyme kinetics without any inhibition. Now you see a very interesting situation here, that if I now vary the inhibitor concentration, what will happen? So if I go to a higher inhibitor concentration, now you see that this is the intercept I have drawn here. But if I go to a higher concentration of the inhibitor, then you can see this value of this x-intercepts will reduce, because actually the inhibitor concentration appears in the denominator. So this intercept will be smaller. Suppose it comes here at a higher inhibitor concentration. However, 1 by Vm, this is unchanged, because this does not depend on inhibitor concentration. So the new curve for an increased inhibitor concentration will be something like this, and if we keep on increasing the inhibitor concentration, it will look like this. So by varying or increasing the concentration of the inhibitor, we'll see a family of curves, but they will all cut the y-axis at the same point. So the y-axis intercept will be the same if we vary the inhibitor concentration, and if we see it, then we conclude that it is a competitive inhibition pathway. Now there could be another situation which we call as non-competitive inhibition, and there another interesting thing happens. You have enzyme plus inhibitor that, as before, have an equilibrium to form enzyme substrate complex that forms the product plus the enzyme back. So here also just remember the enzyme will be back, and then you also have the, this will be substrate, not the inhibitor, enzyme plus inhibitor that is in equilibrium with enzyme inhibitor complex, and plus you can have enzyme substrate adding with the inhibitor to give you the enzyme substrate inhibitor. Now what does it mean actually? So here the enzyme can also have multiple binding site, and suppose I have a shape of the enzyme pockets where the substrate or the inhibitor can bind is something like this. What can happen? A substrate can bind to it, which is fine, and so this will give my enzyme substrate complex, which is something like this, and the inhibitor can actually bind here on this other pocket, which means if I draw it again, suppose this is the shape of the inhibitor, which can now bind here and to give the enzyme inhibitor complex. So this is the EI, this is the ES. The inhibitor can also bind to the already formed enzyme substrate complex. So meaning the inhibitor can further come here and then form something like this. So this is ESI complex because both the substrate and the inhibitor are bound to the enzyme. So this type of enzyme inhibition is known as non-competitive inhibition, and the nomenclature is pretty straightforward because you can see that the enzyme or the substrate and the inhibitor do not compete for the same site on the enzyme because they have very different shape. But now the enzyme can be attacked by the inhibitor or the substrate, and the assumption here is that once the substrate binds to it, then the binding of the substrate causes some conformational change in the enzyme, so that the binding of the inhibitor causes some conformational change in the enzyme, so that this substrate now cannot bind. So there is no such pathway that EI, enzyme inhibitor complex, is going to the enzyme substrate inhibitor complex. So it is inhibiting whenever the enzyme is, whenever the inhibitor is binding. So the only pathway that the product can form is this pathway. So the first step. So we have an interesting third step here. Now you can actually use the similar way. You can actually write an equilibrium constant for this equation. You can write an equilibrium constant also for this equation, and do the material balance very carefully, because you remember that for this case E0 will be the free enzyme concentration plus some enzyme substrate concentration plus some enzyme inhibitor concentration plus some enzyme substrate inhibitor complex concentration. And similarly your S0 will be free substrate at any time plus some enzyme substrate complex. Some of the substrate has been converted to product, and plus you'll have also the ESI complex. And using these two, you can actually figure out what is the value of the steady state concentration of ES, enzyme substrate complex, and now you can put it back into your rate equation, and you can get and write it in terms of the Lineweaver-Burke way, and then you will figure out a very, very interesting equation. This will be like this. Let me write it and then I'll explain what it is all about. Times 1 plus I divided by Ki. Now let us try to plot it in the Lineweaver-Burke plot, which is a plot of 1 over V0 versus 1 over S0. And as before, you will have, say for a typical enzyme inhibitor concentration, I have a intercept. So now the question is, what is this intercept, the y-axis intercept? For y-axis intercept, the x-axis value has to be 0. So 1 over s0 is 0. So this term basically vanishes. So what I'll have is that 1 over v0 will be 1 over vm. So let me just write it somewhere else. So this will be 1 over vm times 1 plus I divided by ki. And then you can also ask this question, what is this x-intercept? So for x-intercept, I'll make this as 0 and ask this question, what is the value of 1 over s0? So if I make that as 0, now you can see that the x-intercept, it will be something like minus 1 over vm, and then I'll have km by vm, but that gets cancelled. And so if that is 0, first of all, you can actually write it. 0 is 1 over vm plus km by vm into 1 over s0 into something, but that something also gets 0 because it's 0 on your left. So I'll have this one. So if I just arrange, this will be nothing but minus 1 over km. Now I have a very interesting situation here. I see that the x-intercept now is independent of the inhibitor concentration because it doesn't appear. However, the y-intercept depends on the inhibitor concentration. If I increase the y inhibitor concentration, so I'll have a value which is more because it is proportional to the inhibitor concentration. So what will happen, I'll have but the intercept x-intercept doesn't change. So what I'll have is that if I keep on increasing the inhibitor concentration, so I'll have something like this. So the curve will be like this. The inhibitor concentration is changing, and you can see that how it is changing. So look at the striking difference between the competitive inhibitor, where we actually did not have this step, we just had 2 steps, and the non-competitive inhibition, where actually had a 3rd step. And look at the curves very carefully. In the case of competitive inhibition, as we are increasing the enzyme inhibitor concentration, we have a common point on y-axis. The intercept is fixed, which is 1 over vm. However, the x-axis intercept, it changes, and the family of curves looks like this. However, the other situation is when we have the non-competitive inhibition, where the x-intercept is kept fixed. However, the y-intercept keeps on changing. We will have more and more y-intercept. So by looking at the curve, whether it is, if we just plot it, the enzyme, the Lineweaver-Burke plot, and if we just ask this question like how it looks like as we vary the enzyme inhibitor concentration, if it looks like this versus if it looks like this, then we can readily figure out what is the nature of the competition. So this will be the competitive inhibition pathway, and this will be the non-competitive inhibition pathway. So you can actually use these equations and try to get the equation of the Lineweaver-Burke form, and see whether you are getting this form. So that you can try, and you just follow the same way like we followed to arrive at this expression. You can look at the these equations. I mean, like how we derived it. It's just simply based on the material balance, which is I have already written here. So what we studied in this entire lecture is that we first started with a mechanism of what is meant by a mechanism, and we talked about 2 approaches. or two approximation. One is known as a rate determining step approximation, and the other one is basically steady state approximation. And we solved very interesting equations, interesting reactions for that. One was this nitric oxide going to NO2, which is apparently simple, but and the rate laws are also simple, but we showed that it can have very different mechanism, both of which can lead to the same observed or predict the same observed rate law. The other one was basically H2 plus Br2 all in gas phase reaction to HBr, which looks very simple, but the rate law was fairly complicated. But we we proposed a mechanism, and that successfully explains the rate law that we discussed. And then we also discussed a little bit discussion on the unimolecular reactions, how unimolecular reactions happen. And we particularly talked about the Lindemann model for the kinetics of unimolecular reaction. Then we talked a little bit about the activation energy or energy of activation, to be more precise. And then we showed how you can think about the kinetically controlled product or the thermodynamically controlled product, and how basically you can control the branching of the product ratios by controlling the temperature or waiting for a long time. And then we switched to catalysis. We gave an example of acid-base catalysis of ester hydrolysis, but most of the time we discussed about enzyme catalysis, and we also discussed what will be the enzyme without any inhibitor and also with any inhibitor. And with inhibitor we showed that there can be competitive and non-competitive pathways. And under the enzyme we actually discussed the Michaelis-Menten equation and how one can get the Lineweaver-Burke plot from Michaelis-Menten equation. So that will be more useful, particularly when you describe the competitive and non-competitive nature of the inhibition. So this concludes our discussion on this lecture on reaction kinetics and mechanism of reaction. So by mechanism, again, it's a model that actually satisfies the observed, or we can more specifically say it is experimentally observed rate law. So that is known as a mechanism, and you can have actually multiple mechanisms for the same reaction. And once you are done, you actually then propose the mechanism, but then actually you also have to verify that this mechanism is correct by trapping the intermediates that we briefly discussed. And then in the next lecture we'll be discussing how one can calculate K from the very fundamental principle. So far we have used K as it is. Only thing we know about K is that K has a temperature dependence, and the expression of K is something like A into e to the power minus A by RT. Now that expression of the Arrhenius law is actually experimentally determined relation. It's an empirical relation because Arrhenius did measure some rate constant at different temperatures, and he arrived at this equation. Now the question is, can we actually develop a model based on collisions between molecules or atoms or atoms and molecules, and then get an equation where we can actually get a form of the rate constant, something like this, the Arrhenius equation. And that is covered under reaction dynamics. That will be discussing in the next lecture. Thank you.